So this is one of the world's strongest men pulling a truck. It's one of the competitions that they have to do. They have to pull a truck that is stationary to begin with, and they have to pull it a particular distance. Once they cross the line, they've finished, and it's the person that can do this fastest wins this particular round of world's strongest man. Now, the question is this chap applying a constant force in the effort to move this truck? And the answer is no. It's hard to get the truck started because of something called inertia. If you've ever pushed a car, you'll have experienced this. It's hard to get the car moving initially, but once it gets going, it's easier to keep it going because of this thing called inertia. This is good because as the event progresses, the athlete will get tired and won't be able to pull as hard. Basically, inertia is the tendency of an object to keep doing what it's doing. So if it's moving, it's a tendency to keep moving. And if it's stationary, it's a tendency to stay stationary. And changing that from being moving to being stationary or from being stationary to being moving can be quite difficult. So in this lesson, we're going to be investigating acceleration. We're going to start with this equation, F equals ma, Newton's second law. We need to rearrange this to give acceleration equals force divided by mass. And this is the thing that we're going to investigate. First thing we're going to do is we are going to keep the mass the same, and we're going to change the force and see how this affects the acceleration. And the second thing we're going to do is we're going to keep the force the same, and we're going to change the mass and see how that affects the acceleration. How does the force on an object affect its acceleration? We're going to do this by setting up a trolley that's attached to a piece of string that goes over a pulley over the edge of a table, and we hang a mass from the string. This produces a downwards force due to gravity, so a weight. This pulls the trolley. And we start with the trolley stationary and we see how fast it accelerates. And there's various ways of measuring acceleration. I won't go into those here. Okay, so an important definition, system. In science, a system's an object or a group of objects that act together. In this case, it's everything that accelerates with the masses that are dropped. So it's the trolley, it's the string, and it's the actual masses that are moving. So when we talk about the system, we mean all of the things that are moving at once. Even though they're not all moving in the same direction, they're still all accelerating at the same rate. So while the direction might be different, the magnitude will be the same for everything. Now, we could make some predictions about this experiment. How does the force on an object affect its acceleration? Well, what do you think will happen if we apply more force to an object? Do you think it will accelerate more, or do you think it will accelerate less? If you said it'll accelerate more, I think you're probably right, but we'll have a look at some results in a little while to find out. Okay, so some questions here. Describe the motion of the trolley when the mass hanging on the string is released. Well, the trolley is going to accelerate forwards or towards the pulley or towards the edge of the desk where the string's hanging. In this case, all the diagrams that we've shown mean that the trolley will move to the right. So anything along those lines that includes a direction. So it will accelerate towards the pulley, towards the right, that kind of thing. What force makes the trolley move? It's the weight of the masses pulling down on the string that pulls the trolley forwards. How does this force vary during the experiment? It doesn't. It's a constant force. Until the masses hit the ground, the force is constant. How could the force on the trolley be increased? Well, we could add more masses to the hanger. And when changing the force, what can we do with the masses to make sure that the mass of the system doesn't change? Now, this one's a little bit more complicated. So the mass of the system is the mass of the trolley and anything on the trolley, the mass of the string, and the mass of the masses hanging on the end of the string. So what we need to do is any masses that we aren't using currently hung on the end of the string, we need to store on the trolley so that they're accelerated along with the trolley. So this means that when we move masses from the trolley to the hanger on the other end of the string, then the whole system stays the same mass. We're not changing the mass of the system because all of the masses are always in the system. They're on the trolley or they're on the hanger, and they're always being accelerated. Experiment 2. How does the mass of an object affect its acceleration? So this setup's pretty much similar. However, this time the mass hanging on the string stays the same. So the force pulling on the string stays the same. So the force pulling the trolley stays the same. What we do is we change the mass of the system. So now we do want to have masses off to one side that aren't part of the system that we can add to see what happens when we add those masses. Now we could make some predictions about this experiment. How does the mass of an object affect its acceleration? Well, now we need to think about if we make a trolley heavier, will it be harder or easier to accelerate? If you said that it would be harder to accelerate, I think you're probably right. Something that's heavy is harder to push. So there are links to a couple of other videos that actually display this experiment pretty well. I'll put those in the description. So as we're not able to do this experiment in person, we've got some results here that have been produced for this experiment. Table 1 is for experiment 1. So you can see the force varies from 1 to 8 newtons, and the acceleration varies from 0.5 to 4.1 newtons. And for experiment 2, the mass of the trolley starts at 20 grams and goes up to 80. And we can see the acceleration starts at 5 meters per second squared and goes to 1.2 meters per second squared. Do these questions bear out our predictions? Yes, I think they do. We start with a force of 1 newton and an acceleration of 0.5 meters per second squared. And as we increase the amount of force, we also increase the acceleration. So as force increases, acceleration increases. And our prediction for table 2 was that as the mass of the trolley increases, the acceleration will decrease. Let's see if that's borne out. It's 20-gram trolley will accelerate at 5 meters per second squared, but an 80-gram trolley, so it's heavier, will accelerate at 1.2 meters per second squared. So that is slower. So more mass means a lower acceleration. So now the answers to the questions. What has the scientist changed in each experiment? So for experiment 1, we changed the force and measured the acceleration. In experiment 2, we changed the mass of the trolley or the mass of the system and measured the acceleration. What has the scientist measured in each experiment? Well, for both experiments, we measured the acceleration of the trolley. Which is the dependent and which is the independent variable for each experiment? Well, hopefully you remember that the dependent variable is the thing that we measure and the independent variable is the thing that we change. So for experiment 1, the force is the independent variable and the acceleration is the dependent variable. And for experiment 2, the mass of the trolley is the independent variable and the acceleration is the dependent variable again. What would you expect to find happen to the acceleration when the force acting on the trolley is increased and the mass of the system is kept constant? Well, we would expect that as force increases, the acceleration would also increase. And the results in table 1 do support this. We ask you to draw a graph of this. And the first thing to do with that would be to plot the points. There are the points. And the next thing to do would be to draw a line of best fit. Now, hopefully it's pretty clear that this is going to be a straight line that goes through the origin, through 0, 0, something like that. What shape is the graph and what does this show? Well, the graph is a straight line through the origin. So this shows that acceleration is directly proportional to the force applied. What that means is that if we double the force, then we double the acceleration. If we triple the force, we triple the acceleration. What happened to the acceleration as the mass of the trolley was changed? As mass increased, acceleration decreased. So this too fits our prediction. And question 9 is sketch a graph of mass of trolley against acceleration below. So sketching involves drawing a graph without properly drawing a graph. We still need a pair of axes, and we still need to label these axes. So we'll have mass and we'll have acceleration. Okay. But we're not going to draw numbers on the axes and scales on the axes. We're just going to give an indication of this. And what happens is we want this sort of shape. And we can tell this because of the numbers. We can tell that when the mass of the trolley is low, the acceleration is high. If we double the mass of the trolley from 20 to 40, we halve the acceleration from 5 to 2.5. And again, if we do this from 40 to 80, we're doubling the mass of the trolley and we are halving to 2.5 to 1.2. It's a bit less than half, but it's more or less halving the acceleration. And we can do this for any pair. So if we take 30 and 60, 60 is double 30. So 3.3 is going to be double 1.7. What shape is the graph? Well, the graph has a negative gradient and is curved. We can say a little bit more about this. We can actually say that acceleration is inversely proportional to mass. Newton's second law of motion states that if a force accelerates an object, then acceleration is directly proportional to the force and inversely proportional to the mass of the object. We should be able to analyze these results to show this relationship. We've kind of done that already. Explain how the results support the statement above. Well, it's to do with the shapes of the graph and to do with what the numbers do. So in table 1, the acceleration doubles as the force is doubled. So it's proportional. It also gives us a nice straight line through the origin. And in table 2, the acceleration halves as the mass is doubled. It's inversely proportional. And again, this gives us the characteristic inversely proportional graph. If the force is tripled and the mass of the trolley doubled, what happens to the acceleration? Well, if force is tripled, this will triple the acceleration. And if mass is doubled, this will halve the acceleration. Remember, what happens to force happens to acceleration. And what happens to mass, the opposite happens to the acceleration. So we need to combine these two. So we need to triple it and then halve it. So if we triple it and then halve it, we make 3 halves of its initial value, or it's 1.5 times larger. I hope that's helpful, and I'll speak to you soon.